This is the part 3 of chapter 5. We are still on the separator. Why separators aren't perfect? We should think about non-ideality of separators in this subchapter. Several causes or reasons are there, and here in this slide I'd like to say about the entrainment in mechanical separation. What is the entrainment? Let me check the meaning of the word entrain. To board a train, so entrain, or of a liquid or gas to carry along, drops of liquid, bubbles, and so on. That is the entrainment. I believe you could understand the meaning of entrainment by solving the example 5.11. Before going to this example, I'd like to emphasize that entrainment happens in mechanical separation, not in thermodynamic-based separation technology or rate-based separation technology. Entrainment is discovered in mechanical separation, and this entrainment causes the non-ideality of separators. Okay, here example 5.11, which is about the coffee making. Situation is summarized here. As you know, this is the filter paper for the coffee, and something is introduced into the coffee filter. And what is that? This is a mixture of liquid phase and solid phase. 33 gram solubles from coffee plus 1,800 gram water is the liquid phase. The other thing is solid phase, and solid phase contains 6 gram solubles in coffee plus 26 gram insolubles of coffee. So it means originally my coffee bean have 26 gram insoluble parts and 39 gram soluble parts. After extracting the soluble parts from the coffee bean to water, then some portion, actually dominant portion of solubles is going to water. However, still the coffee bean has 6 gram solubles with its insolubles of 26 gram. That is the feedstock. Then, of course, liquid coffee is going through the coffee filter. Then finally, you could get the liquid coffee. This is C stream, coffee stream. And the other thing is remaining over the coffee filter. We have two things on the coffee filter. What is that? Grounds, ground coffee or grounds, symbolized by G, and this is the insoluble one plus the soluble material still existing in insolubles. This one is the ground. The other thing is also liquid phase, and liquid coffee is entrained in the solid grounds. So this makes the non-ideality. In the perfect separators, then this liquid coffee is going through the membrane, and then finally you could get this coffee in your coffee cup. However, due to the entrainment phenomena, then this liquid is not allowed to pass through the membrane. Still, liquid is existing with the solid part. So we will calculate those amount. So let me check several amount for this process. The mass of grounds is 6 plus 26, right? That was solid. So 32 gram. So in the stream, G plus L has 32 gram G there. I mean 32 gram grounds there. Also, in the problem statement, liquid entrained with ground is found at 2.5 gram liquid per gram dry solid. It means entrained liquid per ground is 2.5. So we could easily calculate the entrained liquid coffee. Mass of L, while entrained liquid coffee, is 2.5 times of 32 gram. So 80 gram is not passing through the membrane, just remaining over the coffee filter. This is the amount of entrainment. One more things. We could easily calculate the mass fraction of solubles in coffee. I mean C stream. Also, this value is the same as that of mass fraction of solubles in L stream, because that is the coffee. We have already extracted the solubles from the coffee bean, and the concentration are the same for the C stream and L stream. What is that? Extracted solubles was 33 gram, and total amount of liquid is 33 gram plus water amount. Then this mass fraction is 0.018 gram solubles per gram solution. That is the mass fraction. Okay, we have several values are there. And then let me go to the material balance equations. This is the system, and let me assume this system as the continuous flow reactors. So in that case, no accumulation is equal to in minus 2 output stream plus no generation minus no consumption. Therefore, in is equal to out. Let me set up the mass balance equation of in is equal to out for solubles. So in is 39 solubles, 33 gram in liquid, 6 gram in solid. So 39 gram, and is equal to the C stream plus L stream plus G stream. Even if we have one single stream having G plus L, but let me split into two streams like that. So the total summation of the soluble amounts in those three output streams, you could have 39 gram solubles in the feedstock. Then I have said the concentration of C stream, which is liquid coffee, and also concentration of L stream, which is the entrained liquid coffee, have the same concentration, 0.018 here. So you can merge those two things into here. And also the other thing, the ground is actually 6 gram for the solubles. This is the total amount. 6 is 6 gram solubles existing inside of the solid parts. So this is the 6 gram. And then you could calculate the mass of liquid coffee, because we know the value of mass of L stream here. So finally, we could get the coffee at 1753 gram in your big cup. Okay, then we have calculated everything. And the next thing is the recovery. I'd like to compare the recovery of coffee solubles between with entrainment and without entrainment to investigate the effect of the entrainment on the separation. So, fractional recovery of coffee solubles in C stream is some amount of coffee here and total amount liquid. No. Again, the amount of coffee or solubles in C stream per original solubles in feedstock. So feedstock was 33 gram solubles plus 6 gram solubles, so 39 gram solubles. How about the stream C? We have totally 1753 gram coffee. Inside of coffee, you have a solubles plus water. And the concentration of this liquid coffee is 0.018, actually mass fraction. Then you could calculate the amount of solubles in the coffee stream C. So 1.6 gram solubles are there in the stream C. So this value is going to the numerator of the calculation of fractional recovery of solubles in C stream. Then right now we have the value. With the entrainment, you have got the recovery at 81% of coffee soluble. Great, not bad. However, I'd like to compare this value with the fractional recovery of solubles in C stream in the case of without entrainment. The denominator value should be the same because the feedstock is the same, 39 gram. How about the solubles in coffee stream C? Without entrainment, we should have 33 gram solubles in the C. So, if you don't have any entrained coffee liquid over the coffee membrane, then 85% recovery was obtained. Of course, this value is larger than this value. So, entrainment makes our separator non-ideal, and the recovery is going down. And I can say the entrainment is our loss for the desired product. Okay, still, I'd like to ask you, why separators aren't perfect? The second reason is equilibrium. Of course, this course is working on the equilibrium-based separation technology. Entrainment was for the mechanical separation, and equilibrium is for the equilibrium-based separation technology, of course. Phase equilibrium places limits on component recovery and product purity in separation. You could find the similarity for the reactors. You have learned about that. For example, chemical reaction equilibrium places constraints or limits on conversion and yield in reactors. Let me think about some process about the equilibrium-based separation technologies. In feed stream, we have a single-phase multi-component mixture. The total feed rate is like that in moles, and the mass fraction or mole fraction of A and B and C and so on in the feedstock or feed stream. Then it is introduced into a separator. In this separator, two-phase generation and equilibration happens. For example, at the very first time, you have a liquid mixture, and in the separator, you will heat the liquid mixture, then you could make the vapor and liquid. There is some equilibrium between vapor and liquid. So, finally, you have equilibrated phases 1 and 2, or vapor and liquid, and each phase has its own compositions. Like in phase 1, XA, XB, XC, and in phase 2, XA, XB, XC. Of course, these values are not the same between phase 1 and phase 2. Also, temperature and pressure should be fixed to make the equilibrium. Those things are variable for the equilibrium-based separation process. Right now, we have two phases, and then in the second unit, you will separate those two phases. So, to the top stream, you will have phase 1, and in the bottom stream, you have phase 2. So, each composition there, and also the temperature and pressure for phase 1 and temperature and pressure for phase 2 could be different after separation. That is a big picture for the equilibrium-based separation technologies. Okay, before going to the equilibrium-based technology, for some calculation something, I'd like to introduce about the Gibbs Phase Rule. It is a very important thing. Gibbs Phase Rule. Here is the situation. You have a box or container, and at the very first time, you have a liquid mixture for A and B. And then you are trying to make equilibrium at a certain temperature and a certain pressure. Then the single liquid phase is split into vapor and liquid. Vapor has its own composition, and also liquid has its own composition like that. That is the situation, equilibrium situation. A system at equilibrium is specified by variables like temperature, pressure, and composition of each species in each the phase. Then I'd like to ask you about how many variables are independent. I'm saying about the degree of freedom. Gibbs phase rule is the rule to estimate degree of freedom of variables. So let me derive the Gibbs phase rule. Capital Pi is the number of phases present. In this case, 2 you have at equilibrium. C is the number of components present. In this case, we have A and B. That is so 2. F is the number of variables that can be independently set. In other words, F is DOF, degree of freedom. Then let me try to find the degree of freedom from this situation. First one is variables or freedom. Temperature, pressure is variables to specify the equilibrium state. So number 2. And how about the composition? Let me say we have 2 compositions, but the independent composition is just 1 because the summation of those 2 things is going to 100%. If you have a 5 the species, then the independent composition is 4. So C minus 1. That is the variable. So totally, the number of variables is C plus 1. How about restrict? We have phase. And if you have 2 phases, 1 phase equilibrium equations are there to correlate between vapor and liquid. More generally, if you have pi phases, it means we have pi minus 1 phase equilibrium equations. So let me try to calculate the overall degree of freedom. F is equal to C minus 1 plus 2, that is the total variables or total freedom, minus restrict pi minus 1. So here is the final equation, which is known as Gibbs Phase Rule. F, freedom, is equal to component plus 2 minus phase. We'll use this equation to expect the degree of freedom your equilibrium state. Okay, here is the pressure temperature phase diagram of a single component water. So let me look at this phase diagram. Maybe this phase diagram is very accustomed to you guys. X-axis is temperature in Celsius degree. Y is the pressure in millimole. As you know, 760 millimole Hg is 1 atmospheric pressure. And then we have 3 lines. Here, 1, 2, 3. And this area, you can find only vapor. In this area, you can find a liquid water. And this area, you can find only solid, like ice. Between the regions, liquid region, vapor region, and solid region, you have find some lines or curves. So let me start with this one. This line, in this line, you can find vapor, liquid coexistence at equilibrium. So this is the coexistence line between V and L. How about this line? This is V and solid S, VS coexistence line at equilibrium. The other one is, of course, LS coexistence line, or LS coexistence line at equilibrium. So it means this line is about the boiling or condensation. This line is relevant to the sublimation. Or this line is about the melting or freezing. Two more things. I'd like to say about 2 points. This point. At this point, you can find the solid, you can find the liquid, and you can find vapor. It is so-called triple point. For the case of water, temperature is around 0 Celsius degree, and pressure is very low pressure, like 4.6 millimole. One more point is there. It is so-called critical point. In this region, you would have the supercritical fluid. Which is not the liquid, which is not the vapor, of course, which is not the solid. So this critical point is found at 380 Celsius degree. Also very high pressure, like 1.7 by 10 to the 5 mmHg. So I have explained about some characteristics of pressure temperature phase diagram of water. Then let me use the Gibbs phase rule for checking the degree of freedom. Pure water, maybe here, water means liquid water, then single component and single phase, of course. So freedom is equal to one component plus 2 minus one phase. So freedom is 2. What does it mean? What does it mean? Two independent variables are available, which should be temperature and pressure. So I have said we have two variables. So pure water is found in area because we have two variables of temperature and pressure. So only liquid of water is found in this area. In the same for vapor. Vapor is found in the area because temperature and pressure can be variable or varied. Solid is the same. So single phase is found in the area based on variable temperature and pressure. Let's go to the second thing. Pure water as both vapor and liquid. It means you could find this guy on the line of vapor liquid coexistence curve. And in this case, let me calculate the freedom also. Single component, just H2O, but two phases. So one single component plus 2 minus 2 phase is going to 1. It means only one independent variables are allowed. Temperature or pressure. For example, pressure is determined at a fixed temperature. So only single variables are allowed. It means those two phase situation is found on the line, like vapor liquid coexistence. Because if the temperature is fixed, then pressure should be fixed. It means that is the line. Then the same thing is applying for the liquid solid coexistence and VS coexistence line. Let's go to the triple point. In this triple point, you have solid, liquid, vapor, so 3 phases. But still single component. Then freedom is equal to one single component plus 2 minus 3 phases is going to 0. It means 0 independent variables. It means temperature and pressure are already fixed. You cannot change something. So it means in this temperature and pressure diagram, you can find point. Not the line, not the area, only point, because the freedom is just 0. And you cannot change the value of pressure and or temperature at triple point. So I have calculated it already. Then still we are on the same pressure, temperature, phase diagram of water. Everything is the same. Again, here vapor liquid coexistence line. Here liquid solid coexistence. This one vapor solid coexistence line. And let me check some points in this pressure temperature diagram. Let me start with this one. So this point is found on the coexistence line of vapor and solid. And we could say we have a saturated vapor and a saturated solid at this point. At let me say minus 50 Celsius degree and 10 to the minus 2 milli Hg. So when you are saying about the vapor, solid, liquid at the equilibrium line, then you should put the saturated. Second one, saturated vapor, saturated liquid, because this is the coexistence curve of vapor and liquid. And on the solid liquid equilibrium line, then you could find saturated liquid, saturated solid. I mean, two phases are there. Okay, so let me change some temperature. The starting point is here at minus 90 Celsius degree and 10 to the minus 2 milli Hg. Then let me increase the temperature at this fixed pressure, very low pressure, 10 to the minus 2. Then this water would experience some passing through the equilibrium situation, then finally go to the only vaporism. And this vapor is so-called superheated vapor, because this vapor is going from the equilibrium point when it is heated. So superheated vapor. Also, at this point can be read at 250 Celsius degree hot temperature and about 10 to the 4 milli Hg high pressure. Then let me cool down this water vapor. Then this point is passing through the equilibrium line, finally reach this point. And this point is subcooled liquid. One more things. I have said we have three equilibrium line. This one, this one, this one. Specifically, this liquid vapor equilibrium line can be described by an empirical equation, which is called Antoine's equation. Let me think about Antoine equation here. Log 10 saturated pressure, because we are on the coexistence line, is equal to some parameter A minus B parameter per T plus C parameter. Of course, T is the saturated temperature. And the parameter value of ABC was already empirically determined. Then you could get these values from any internet or database, and also the appendix B in our textbook. So this line can be described by this equation, and after finding the A and B and C for your material, then you could calculate the saturated pressure from temperature or saturated temperature from your saturated pressure. Here is the multi-component systems for Gibbs Phase Rule. So, two component and two phase system such as ethanol water mixture in a container is the situation of this slide. Here is a container, and you have a mixture of ethanol for E and water for W. At some temperature or at some pressure, this mixture is separated into liquid and vapor in the container. Each phase has its own compositions. Like for a liquid phase, we have composition of ethanol, Xe, and composition of water, Xw. Usually, X symbol is used for liquid composition. I have said about that before. And in the vapor phase, you have also another composition of ethanol and water. So Y sub E, Y sub W. Y is the symbol for the vapor phase composition. So here is the four variables. Temperature should be specified, and pressure specified, and the composition of ethanol in liquid, or sometimes the composition of water in liquid could be considered as the variable. But you cannot use both of them because this one plus this one is going to 100%. So only one composition is independent variables. And the other thing is vapor composition of ethanol or water. So we have four variables here. Let me check the freedom, degree of freedom, by using the Gibbs Phase Rule. F is equal to component, here's the 2, ethanol and water, 2 plus 2 minus number of phase, so 2 phase, so it is going to 2. It means 2 independent variables can be specified from 4 possible independent variables. That is to say, if you have specified temperature and the vapor composition of ethanol, then pressure and the composition of ethanol in liquid are fixed. So then let's go to the multi-component systems. Two-component liquid-solid phase equilibrium. Here, I'd like to introduce liquid-solid mixture case about the liquid-solid phase equilibrium. Imagine the seawater. We have sodium chloride inside of water. So that is the liquid-solid mixture. Of course, after sodium chloride is totally dissolved in water, then we could consider the solution as one single phase. However, when you change the temperature, you could split the single phase solution into saturated solution plus precipitated solids. The solubility of most solids, like seawater, is a function of temperature. However, practically independent of pressure. So usually we don't need to think about the pressure for the liquid-solid phase equilibrium diagram for the liquid-solid mixture. So usually we use the temperature composition diagram instead of temperature pressure or something. This temperature concentration diagram is called solubility curve. So here, solubility curves of several salts in water presented. X-axis is the weight fraction of salt in aqueous solution. So the unit of which is gram salt per gram solution, from 0 to 1. 0 indicates no salt in water. However, 1 means only salts are there without any water. Y-axis is the temperature. because the solubility is changing with temperature. We have three different sorts, and then I'd like to focus on this line, which is about the solubility curve of potassium nitrate. So you can easily recognize that the solubility is increasing as the temperature goes up. For example, at 20 Celsius degree, the solubility of the KNO3 in water is about 0.25 gram salt per 1 gram solution. However, when you increase the temperature into like 100 Celsius degree, the amount of salt dissolved in water is increasing into 0.7 gram salt per gram solution. Then let me think about the area on the right side of this solubility curve. Of course, you have higher concentration than the solubility in this curve at a fixed temperature. For example, at 60 Celsius degree, you could read the, for example, about 0.5 solubility. However, in this area, on the left side of this curve, you have higher concentration, like 0.8, than the solubility 0.5. So, some portion of salt is precipitated because its concentration is higher than the solubility. So in this region, you have saturated solution, of course, plus solid salt undissolved from the saturated solution. So this region is two-phase region. However, on the left side of this curve, we have unsaturated solution because the amount of salt is below the solubility. So this right region is single phase region. That is the solubility curve for salts in water. And let me think of the other cases for the ammonium chloride. Different, but the trend is the same. Like as temperature is going up, then solubility is going up. However, in the case of sodium chloride, the solubility of sodium chloride looks independent of temperature. For any temperature between 0 to 100 Celsius degree, the solubility is about 0.26 gram sodium chloride in 1 gram solution. It looks great because in nature we have sodium chloride solution here and there, like ocean, seawater, and even some electrolytes in our body and living organisms. If the sodium chloride solution is if the solubility of sodium chloride solution is significantly changing with temperature, then what happens? It is a kind of tragedy. We could have a salt of sodium chloride precipitated from our electrolyte in our body, or sometimes in seawater. So, nature chooses the sodium chloride solution as electrolyte in our nature. How beautiful and how great our nature is. Still, we have the same solubility curve here. X is the salt concentration, Y is the temperature. This curve is for the KNO3, potassium nitrate in water. It's a solubility curve. So, I have said Left side, we have a single phase region. Right side, we have two phase region, having saturated solution plus solid. We don't have anything for calculation because only single phase. Everything is just an unsaturated solution. There are no solid there. However, in this region, we need to calculate the amount of the saturated solution and its mole fraction or mass fraction, and also the amount of solid and its mole fraction or mass fraction. How can we calculate those values? We could calculate them easily by using this solubility curve or temperature composition curve diagram. So here is the point. I mean, we have 0.5 gram potassium nitrate salt in 1 gram solution at 30 Celsius degree. Then how many amount of solid and liquid for each phase? So let me calculate the composition for the saturated solution and the solid at the first time, and then we'll go to the amount of each phase. I have said we are on the 30 Celsius degree. Then this point is split into 2 points at the same temperature. One is here and the other is here. This curve is about the saturated solution, right? This is the solubility curve. It means saturated solution. This vertical line, actually y-axis, on the right side, indicates the solid line. So from those lines, you could calculate the composition. Again, the composition of GA was the 0.5. Then this composition is split into two compositions. One is found on the solution line and the other is found on solid line. Then just read the value about the wave fraction of potassium nitrate. Then going down there, and the value is 0.31. This value is the composition of salt in the saturated solution, because you have read the value about the liquid curve. How about the composition of solid? So you have this point, and then going down you could read 1. Of course, I have said about the solid. So the composition of the salt in solid should be 100%. So the weight fraction of solid is 1. Okay, right now I have had the information about the weight fraction for solid phase and liquid phase. Then let's go to the amount, percentage amount. The length of this one or the length of this one is for the amount for solid and liquid. Which length is for which one? We should determine that. So actually for the compositions, just you have read the value about the liquid, and then that is the liquid composition. Or you have read the value from the solid curve, then the value is about the solid. However, the mass of each phase is different. This line, I mean the length of this line, is closer to the solution line or solution curve. However, this length is not for the solution. This length is for the solid. And also, this the length of this line closer to the solid is not for the solid. Actually, this is for the liquid. So, for the mass of each phase is following the inverse level rule. I'd like to emphasize the word inverse because this length is for liquid and it means this is for the other curve and this length is for the solid which is far from this line. So it is called inverse level rule. Inverse. So let me try to calculate the amount of solid and amount of liquid. Forget this equation. It is not very useful. So just try to read the values from the temperature composition diagram. Okay, let me start. I'd like to measure or estimate the amount of solid. So this line between XAL to ZA is far from the solid curve, right? Solid composition curve. So it is the solid. It is for solid because the amount of each phase is following the inverse level rule. And this line is for the liquid. So the amount of solid is this length far from the solid line. So 0.5 for ZA here and 0.31 for XAL. So 0.5 minus 0.31 is going to this solid line, solid length. Per the full length of this line indicates the total amount of solid plus liquid. So 1 minus 0.31. 1 minus 0.31 is going to 27.5%. That is to say, 27.5% of total amount of solution plus solid is going to solid, precipitated from the solution. Of course, how about the amount of liquid? The rest of them. So 72.5%. Or you could calculate the amount from this length. 1 minus 0.31. No. 1 minus 0.5 here, and the total length here is going to 72.5%. Okay, so if you know the value about total amount like 100 gram, then you could say that 27.5 gram of solid is precipitated from this supersaturated solution. That is the inverse level rule, and this kind of rule can be applied to other situations. It's very important thing. Please remember it. However, you don't need to memorize the inverse level rule. Please remember it, but remember this calculation. Again, however, you don't need to memorize. Here is another example about the two-component liquid-solid phase equilibrium about the liquid-solid mixture case. Here we have two molecules. One is benzene, and the benzene is liquid at room temperature. How about naphthalene? Naphthalene is solid at room temperature. They look similar to each other. So for chemically similar two components, usually they are miscible or dissolved to each other readily. So we could expect one single phase solution of benzene with naphthalene. So let me think about the temperature composition diagram. It is very similar to the previous temperature mole fraction diagram. for the case of potassium nitrate in water. However, it is even more a little bit complicated. X-axis is the mole fraction of naphthalene, which was solid at room temperature, and Y is the temperature as you expected. You don't need to think about the pressure for the case of solid dissolved in liquid. Okay, so x-axis is mole fraction naphthalene, so 0 means only benzene. So this vertical y-axis is considered as the benzene line. How about the value of 1 for the mole fraction naphthalene? It means we have only naphthalene. So this vertical line is considered as the solid naphthalene line. Between them, we have some complicated situations. On the y-axis, for the benzene line, you could find the melting point of benzene here, about 5 Celsius degree. Then, when you decrease the temperature below the 5 Celsius degree line, the benzene is crystallized into solid benzene. In the same way, above the melting point of naphthalene, naphthalene is liquid. However, below the melting point of pure naphthalene, like about 80 Celsius degree, then naphthalene is going to the solid naphthalene. In the case of pure 100% naphthalene case. However, in a mixture of benzene in naphthalene, the melting point or this line is going down. So the melting point is decreased into here. At the same time, the melting point of benzene is going down. Those two curves are met at one point, showing the minimum temperature of the melting point. This point is called eutectic point. Let me read the value about the eutectic point. 0.14 mole fraction around here for naphthalene, and the temperature is -4 Celsius degree. So I could say the mole fraction is eutectic mole fraction and the temperature is eutectic temperature. Below the eutectic temperature, all benzene and naphthalene mixtures are in solid phase. Look at this area. In this area, you have a single phase, which is the solid. In any mixture between benzene and naphthalene, all of them is going to the solid. However, between the one single liquid phase in this region, also this region for the solid benzene plus solid naphthalene, you could find another region. Those two regions have two phases. Let me start with the right one. In this area, you could find saturated solution of naphthalene in benzene plus solid naphthalene. You could recognize that this area or region is closer to the solid naphthalene line. So you would prefer solid naphthalene rather than the solid benzene. However, in this left region, you will find solid benzene with saturated solution of naphthalene in benzene. So those two areas can be classified as the two-phase region. So it is a little bit more complicated than the previous temperature mole fraction diagram. Based on understanding the eutectic diagram about the naphthalene in benzene, let me try to calculate some values about the composition and the amount of each phase. Again, you have single phase region for liquid here, and another thing is the single solid phase region. Between them, you have two phase regions here and there. So, in the two phase regions, we should calculate the mole fraction and amount of each phase. In this case, right now, we have 6 gram mole naphthalene, N, symbolized by N, and 4 gram mole benzene, symbolized by B. Initially at 80 Celsius degree are mixed. So this point, here is the 80 Celsius degree, and the naphthalene mole fraction is 0.6, which is calculated from 6 naphthalene per 6 plus 4, so 0.6 mole fraction of naphthalene. So here is the 0.6. The starting point is here. And let me cool down the mixture going to 20 Celsius degree. So this mixture is following this line, and we are passing through the equilibrium point or solubility limit here. Then finally we are going to the two-phase the area between the saturated benzene and plus solid naphthalene. So let me try to calculate the amount plus some mole fraction for each phase. This point is split into 2 points at 20 Celsius degree. So one is going to here on the solubility curve of naphthalene in benzene. Also, the other point would be found on the line on the solid naphthalene line. So you could easily the composition for each phase easily. Just read the point, the mole fraction of point. In this case, I'm saying about the saturated solution of naphthalene in benzene. Then the mole fraction of the solution is about 0.27 naphthalene in benzene. How about the solid part? Of course, 100%. So the mole fraction of the solid phase is 1. And then let's go to the amount of each phase. Here is the solid phase line, or actually solid naphthalene. So therefore, far away from this vertical line, you could find solid length, solid line. So the length of this solid line is going to the amount of solid. And the other line is for the solution. I'm saying about the inverse level rule. So this line is responsible for the amount of saturated solution of naphthalene in benzene. Then let me calculate it. The amount of solid is about this one, 0.6 minus 0.27 per total length, 1 minus 0.27. Then 45% of total amount is going to the solid, pure naphthalene. And the amount of liquid could be calculated from this length. It means 1 minus 0.6 per the total length of this line, 1 minus 0.27. Then it is going to 55%. So we have if we have 100 gram of total solution plus any solid content, then 45 gram is going to the solid and 55 gram is going to the saturated liquid, at which we have the mole fraction of naphthalene is 0.27. That is the inverse Laval rule. You have learned about the two-component solid-liquid phase equilibrium in the previous several slides. And then it's time to go to two-component, the same, but vapor-liquid phase equilibrium of liquid-liquid mixture case. Again, in the previous several examples, you have learned about the solid liquid phase equilibrium. Right now we are going to vapor liquid phase equilibrium. Okay, so the composition of the phases in this case is sensitive to both temperature and pressure. Can you remember? For the solid liquid phase equilibrium, pressure is not important, but right now we are thinking about the vapor instead of the solid. So in that case, both temperature and pressure are important. It means we have three variables: temperature, pressure, compositions. Also, it means we need to have three-dimensional phase equilibrium diagram. But it is very difficult to understand the three-dimensional diagram. So practically we have the following two graphs. The first one, the plot of temperature and composition diagram at constant pressure, or the second, the plot of pressure composition diagram at constant temperature. Here's the example of the vapor liquid phase equilibrium diagram. Of course, that is the temperature and composition diagram. This is about the ethanol and water mixture at pressure equal to 1 atm. So x-axis is the mole fraction of ethanol and y-axis is the temperature. So this is the temperature composition diagram at constant pressure. Let me check the 0 point for the mole fraction ethanol. It means we have only water. So this vertical line can be considered as the pure water line. So you could find the boiling point of water in this vertical line or y-axis. Then when you decrease the temperature from like 110 Celsius degree into below 100 Celsius degree, vapor phase is converted to liquid phase for the pure water. Let's go to the other extreme. At mole fraction of ethanol is equal to 1 means that is the pure ethanol. And what is the boiling point of pure ethanol? Here, like that, about, I'm not sure, 78.5 Celsius degree is the boiling point of pure ethanol. So when you cool down the temperature from some temperature here to below than the boiling point of pure ethanol, of course the vapor phase is converted to liquid. So right now we have a vapor and we have a liquid. Between them we have two phase regions, and the below curve is called bubble point and the above curve is dew point. Why it is called dew and why the other curve is called bubble point curve? Okay, when we go from vapor phase into two phase region, then at this point or at this boundary you will meet the first liquid droplet in the vapor. So what is the liquid droplet in air? It is called dew. So this line is called dew point line. And you could calculate the dew point temperature or composition at this line. How about bubble point? When we go from liquid region to two-phase region, the first gas bubble or vapor bubbles is found in liquid, so it is called bubble point curve. Okay, that is the temperature composition diagram of ethanol and water. I should say one more point, which is called azeotrope point. This azeotrope point is intersection of dew point and bubble point curves. The boiling point of mixtures is minimized at this azeotrope point, and also at this point vapor and liquid compositions are the same. Let me try to read a vapor liquid temperature composition diagram. Of course, also in this example, you will use the inverse level rule for calculating the amount of each phase. Let me follow this illustration statement. A mixture of 40 mole percent ethanol, 60 mole percent water at 77 Celsius degree is a subcooled liquid. Okay, so what is the Z with subscript E or ethanol? That is the 0.4 because 40 per 100, so 0.4. And temperature is 77 Celsius degree. Then let me find that point in this temperature, the mole fraction diagram. 77 and 0.4 here. And then so this point is a subcooled liquid below the bubble point curve. We raise the temperature, and then it means this point is going up and cross the bubble point curve at 80.5. Okay, so this point is going up. Finally, we could meet the bubble point curve. So at this bubble point, the ethanol mole fraction in the saturated liquid phase is the same as the mixture mole fraction, that is to say 0.4. Okay, so let me focus on this point. So right now we are on the boundary of the two-phase region. So let me consider this point like the point in the two-phase region. So it means we will split this single point into 2 points. One is going to the right, and then finally we have the point on the bubble point. Also, the other thing is, the other point is going to the left, so we have the same point, the same point of the original point on the boundary, still on the boundary. So, and you could read the composition of liquid from this point, and the composition of a vapor is read from this point. So it means the saturated liquid have 0.4 mole fraction of ethanol. However, the vapor has ethanol at 0.6 mole fraction. So right now we have understood the point of this one. Anyway, even at this one we have two phases. One is liquid and one is vapor. Then let me increase the temperature more, and then finally we are at 85 Celsius degree. So right now the point within the points are within the two-phase region. And then after splitting this single point into 2 points, then you could read the mole fraction for each phase, and then by applying the inverse level rule, you could calculate the relative amount of each phase. So let's do it. So this curve is, what is that? Bubble point curve. No, right. Bubble point curve. Also, this line is for the liquid. And this line is the dew point curve for vapor. So the single point is split into 2 points, and from this point you could read the composition of liquid, and from this point, beta point, you could get the information, that is to say the composition of vapor. You are not applying the inverse level rule in the case of this composition, right? Can you remember? So the liquid composition of ethanol is about 0.13. So XA, alpha is liquid, is 0.13. How about the vapor phase? So vapor phase, you have about 0.48 mole fraction of ethanol in water vapor. So 0.48. Then let's go to the amount for each phases. It's time to apply the inverse level rule. This is the vapor side, and this curve is for the liquid side. So this length is responsible for the vapor amount, and this length is responsible for the liquid amount. So let me calculate it. So about the beta or vapor, 0.4 minus 0.13, this length, and per the total length or full length between alpha and beta, 0.48 minus 0.13. Then I can say 77%, 77 mole percent is going to the amount of vapor. How about the liquid? This length per the full length, like 0.48 minus 0.4 per 0.48 minus 0.13, then it is going to 23 mole percent, which is responsible for solid. That's it. Multi-component gas-liquid phase equilibrium. At the very first time, we have learned about solid liquid and then liquid. Then this is the third case about the multi-component gas-liquid phase equilibrium of gas-liquid mixture case. The solubility of the gas in the liquid phase depends on both temperature and pressure, like liquid mixture. So here is the pressure composition diagram of SO2 gas in water with 4 isotherms. So x-axis is the composition of SO2 in liquid phase, and y-axis is the partial pressure of SO2 in vapor phase. So let me think about this situation. We have a container and water, and also some liquid is there. We have 2 phases here, and liquid phase has some SO2, and the composition of SO2 in liquid is X with the subscript SO2. And also vapor phase has its own composition. There is Y with subscript SO2. So this XSO2, I means the liquid composition is going to the x-axis, and x the vapor composition of SO2 is going to y-axis. But it is not exactly YSO2. Instead of it, we have used the partial pressure of SO2. This partial pressure SO2 is easily converted to the composition of SO2, actually mole fraction of SO2, by using this partial pressure equation. Partial pressure is the product of mole fraction of the corresponding species with total pressure. So if you know the total pressure, you could easily convert the partial pressure of SO2 to the mole fraction of SO2 in vapor phase. So again, the liquid part is going to x-axis, and the vapor part is going to y-axis. So right now we have pressure and composition. One more thing, temperature. I have said the solubility of the gas in the liquid phase depends on both pressure and also temperature. So in this pressure composition curve, the diagrams, we have 4 different curves which is specified as several temperatures. This curve is called, each curve is called isosome, which is defined as the curve at a specific temperature. It means we have 4 different isosomes. The first one is isosome at 0 Celsius degree, and this one isosome at 10 Celsius degree, something like that. Then we have this kind of curve. It means as partial pressure of SO2 in vapor phase increases, then the liquid composition of SO2 increases. Of course, more amount of SO2 in vapor phase, and then of course for at equilibrium you have more amount of SO2. One more thing, temperature. When temperature goes up, then the solubility of gas SO2 in water decreases. It means at higher temperature, the SO2 molecules dissolved in water is thermally more activated. So these molecules are trying to escape from the liquid into vapor. So at higher temperature, you have lower solubility of SO2 in liquid phase. Then let me read the gas solubility graph. Here is the same graph for the mixture of SO2 in water. And we have 4 different isosomes in partial pressure versus composition diagram. Let me follow the illustration statement. Number 1 case, a gas mixture at 1320 mmHg and 10 Celsius degree. So this is total pressure, and this is the temperature. Contains 9 mole percent SO2 and 91 mole percent nitrogen. That is to say, partial pressure of SO2 should be calculated to use this diagram. So the partial pressure is P sub SO2 is equal to the vapor composition of SO2 with pressure. So the statement is saying that 9 mole percent SO2 in vapor phase with total pressure like that. Then pressure is equal to 120 milli-mercury. It means this is y-axis, y point, and 10 Celsius degree is indicating the curve of isosome. So starting point is 120 millihg, and the horizontal line is going to the 10 Celsius degree here. Then you could easily read the solubility of this point. What is that? That is the about 2.8 kilogram SO2 per 100 kilogram H2O, like that. So at this at this partial pressure and at this temperature, you have the solubility at 2.8 kilogram per 100 kilogram water. That's it. And let's go to the second one. An aqueous solution containing 10 kilogram SO2 dissolved in 100 kilogram H2O. Here 10 is equilibrated with air at 10 Celsius degree and 760 millimole Hg. 10 Celsius degree means we need to use the vertical line reaching the 10 Celsius degree isotherm. So right now we are here, and 760 millimole mercury indicates the total pressure. From this point, we could obtain the value of the partial pressure of SO2 in vapor phase. The value is about 470 millimole Hg. So, which is divided by 760 millimole Hg as a total pressure. Then you could calculate the mole fraction of SO2 in vapor phase. That is the 0.62 or 62 mole percent. You have learned about the phase diagrams until now, and by using the phase diagrams, you have calculated compositions and amounts distributed over multiple phases. So, you are recognizing that the phase diagrams are very useful. Until now, you have 5 different phase diagrams in previous slides. Let me summarize them. The first one, single component 3-phase diagram in pressure temperature coordinate for water cases. So in this diagram, you have 3 single phase regions plus 3 2-phase lines or curves plus 1 3-phase point for the single component phase diagrams. The second one was 2-component solid liquid phase diagram in temperature composition coordinate for the potassium nitrate in water case. So here, then 2-phase regions. Sorry. So 1 single phase region, unsaturated solution, and 1 2-phase region, saturated solution plus cobalt salt, you have found in this phase diagram. And let's go to the third one, 2-component solid liquid phase diagram in temperature composition coordinate. The same with the second one. However, we have used in this diagram naphthalene in benzene for this one, and in this case we have a more complicated temperature composition coordinate or diagram. The two-phase regions, like that, this one and this one, between 2 single phase regions. So unsaturated solution, this is single phase, and the other thing is everything is solid region. So we have those areas are there. And one more things, we have one eutectic point in this case. The fourth one is 2-component vapor liquid phase diagram in temperature composition coordinate of ethanol in water here, and 1 2-phase region between 2 single phase regions with an azeotropic point. And the last one was two-component gas-liquid phase diagram in temperature composition coordinate of SO2 gas in water case. So here, and each line is called isosum, and isosum is used to correlate compositions between liquid phase and gas phases. So we have some experience of various phase diagrams until now. Phase diagrams are made up of experimental data. What if the data is not available? In other words, what if you do not have phase diagrams? In that case, if theoretical or empirical equations are available, it is the second best. Of course, the best is the phase diagrams. But sometimes these equations are more useful than the phase diagram when you are using a computer for calculation. So let me assume we don't have phase diagrams, and then let's go to the equation to describe some equilibrium between different phases. The first equation is Raoult's law. Raoult's law is for vapor-liquid equilibrium. Please remember, Raoult for vapor-liquid equilibrium. For vapor-liquid equilibrium, we could use this equation, which is the Raoult's law. Partial pressure of species I can be described by the vapor phase composition. On the other hand, also the same thing can be calculated by the liquid phase composition. So, by using this equality, you could correlate between the vapor phase composition and liquid phase composition. That is the Raoult's law. So by reshuffling here and there, then vapor phase composition Y of species I is proportional to the liquid phase composition Xi, and the coefficient can be calculated by total pressure and the saturated pressure of species I. Again, this Pi set is the saturation pressure of pure component I. So this value, this pressure can be calculated by Antoine equation you have learned about before. So anyway, so this Raoult's law is applicable to a system in which molecules in the mixture are similar in size and chemical structure, so that no strong interaction between the molecules is available. For example, this Raoult's law works for hexane and heptane, looks similar size, similar chemical structure, and benzene and styrene or something like that. However, it does not work for ethanol and water because of their strong hydrogen bonding interaction. That is the strong interaction. But for using Raoult's law, we cannot allow the strong interaction between the molecules. And also, it does not work for polystyrene in benzene because they are too different in terms of size. Also, Raoult's law can be used only when both vapor and liquid phases coexist in equilibrium. So, this equation is for the equilibrium between vapor and liquid. How to use Raoult's law? So the first case, is about how to calculate the compositions at a fixed temperature and pressure. Even if we don't have phase diagram, let me imagine a phase diagram. This phase diagram is simulated by actually Raoult's law by myself about the hexane and heptane. Let me symbolize hexane by 6 and heptane by 7 because they have 6 carbon and 7 carbon respectively. So this is the temperature composition diagram. X-axis is the composition of hexane, so X6, or sometimes Y6. X for liquid phase composition, Y for vapor phase composition. And Y-axis is the temperature, of course, and we have liquid region where the both components are all liquid, and we have vapor region for both compounds. Between them we have two phase regions at which two phases coexist. So our objective is to calculate the Xi and Yi at a fixed temperature and pressure. As you know, temperature composition diagram would be given to you at a fixed pressure, right? So let me say this is obtained at fixed pressure, 1 atm or something like that. And also temperature is fixed. So if you have the phase diagram, then you could easily find the value of liquid phase composition and vapor phase composition. But here I will use the Raoult's law, not by using the phase diagram. So the first thing here, calculate the saturation pressure of hexane and heptane from Antoine equation at the given temperature. So we have real values about that, maybe two values for hexane and heptane. Then you could use those values for the Raoult's law. Use Raoult's law at the given pressure, total pressure. So pressure was given, so this is given right now after the first step, and this is the value given to you in the problem statement. So this is constant value. And so you have Raoult's law for hexane, and also you have Raoult's law for heptane. So you have two equations, and two more equations are there. The summation of all x is equal to 1, and the summation of all y vapor phase composition is equal to 1. So we have 4 equations. Equation is equal to 2 Raoult's and 2 summation. How about freedom? Well, the number of variables. X6, I mean the liquid phase composition of hexane and vapor phase composition of hexane, and also liquid phase composition of heptane and vapor phase composition of heptane. So 4 freedoms. 4 minus 4 is going to 0. Degree of freedom 0. So by using those equations, you could calculate all of the variables about the compositions of two components. Then you could calculate Xi and Yi. Let's go to the other case. How to calculate the bubble point or bubble point temperature and dew point or dew point temperature at a fixed composition. So also in this case, let me start with the phase diagram, even if you don't have a phase diagram. At a fixed, the composition of hexane or heptane, anything is okay. Let me say 0.4 heptane. We could find 2 points on the curve for the bubble point and dew point lines. The blue one is bubble point, of course, and the black one is dew point. Then at these compositions, you could calculate the bubble point and you could calculate the dew point. Of course, if you have a diagram, this diagram, you could easily find the dew point and bubble point at a fixed composition. However, right now we don't have any phase diagram, so we will use the Raoult's law to calculate the bubble point and dew point. So let me start with the bubble point. The given composition Z6 is the liquid phase composition for the bubble point. I'm saying about this one because on the bubble point curve you could find the bubble point temperature, right? And the bubble point is on the side of the liquid, and the composition of this point is for the liquid phase composition. So the given composition Zi or Z6 is equal to X6. X indicates liquid phase. G indicates the given one. Okay, then let's go to the second step. Describe saturation pressure of hexane or sometimes heptane as a function of temperature by Antoine equation. Then use the summation equation of vapor phase composition. So liquid phase composition was given to you. Of course the summation is going to 1, but everything is given to you. But the vapor phase composition is calculated from the Raoult's law having Antoine equation. So the summation of Yi vapor phase composition is equal to 1 can be used for the calculation. Then Yi is equal to like Raoult's law, and Pi saturated is the function of temperature by Antoine equation. Then when I put this equation into the summation, finally we would have total pressure is equal to the summation of the given composition with saturated pressure. The total pressure is given, right? And Zi or Xi is given, and this Pi saturation pressure of each species is the function of temperature. Then in this equation only unknown is temperature, then you could obtain the value of temperature, which is the bubble point. So you have to find the bubble point like that. How about dew point? Dew point is found on the dew point curve, which is on the side of vapor. So the given composition Zi is the vapor phase composition, not the liquid phase composition. And then the same thing, describe saturation pressure of each species as a function of temperature by Antoine equation, and use the summation equation of liquid phase composition, like summation of Xi is equal to 1. Then put the Raoult's law into here with the Antoine equation. Finally, we have obtained this equation. 1 over total pressure is equal to the summation of the given composition per saturated pressure. This is given, some value here, and Pi saturated have only function having unknowns, that is the temperature. So this temperature is going to dew point. Then you could calculate the dew point. Here is the real example how to find or calculate the dew point and bubble point temperature of hexane heptane mixtures. Example 5.12. So we have 0.4 x6. Okay, this diagram is not given to you for calculating the dew point and bubble point, right? So in this is the reference for you for understanding, helping you understand the situation. But anyway, we have right now the 40 mole percent hexane and 6 mole percent heptane at total pressure is 2 atm. Then question is, what is the dew point and bubble point temperature? 6 for hexane and 7 for heptane, and here's the Antoine equation for hexane and heptane. Of course, A, B, C values are obtained from Appendix B or in any database of internet. In this case, temperature in Celsius degree and pressure in milli Hg. Then let's go to the dew point. At the dew point, the given composition is vapor phase composition. Dew point, the blank line, dew point is on the side of vapor, and the given composition G6 while G7 is the vapor phase composition. So Y6 and Y7. So 0.4 and 0.6. Here is the Lars law. So Yi is given like 0.4 and 0.6, and here's the total pressure. In this case, total pressure should be described by the unit of milli instead of atm. So 1520 milli Hg. And that is the Antoine equation for the hexane and for the heptane. Then we have three unknowns or variables, x6, x7, and temperature. One more equation is here. x6 plus x7 is going to 1, right? Then we, after reshuffling each equations in terms of x6 and x7, then summation of those things should be 1. So right now we have only single unknown here, temperature. By solving this equation, you could obtain the temperature. This temperature is the dew point, 114 Celsius degree. Then, by using the temperature, you could also calculate the composition of the liquid phase composition of hexane and heptane. So 0.234, 0.776. In this diagram, x6 at dew point is here, this one. So 0.234. Let's go to the bubble point in the same way, but you should recognize that at the bubble point, the given composition G6 or G7 is the liquid phase composition, S6, X7. Please compare between the solution, compare the solution between the dew point and bubble point. Only different thing is this one. Here, Y6, Y7 has the value, but in the second case of the bubble point, X6 and X7 has the value. Then the same Lars law, and the summation of vapor phase composition is equal to 1. Then you have some equations, and then finally you go to the bubble point. That was the 108.5 Celsius degree here. And then at this temperature, you could calculate some composition of liquid phase. So that is the Y6, this point. That's it for the Raoult's law. Here is the second equation, which is Henry's law for gases dissolved in a liquid. Henry's law is applicable to a system characterized by low concentration. I'd like to emphasize low concentrations of non-condensable gases dissolved in a liquid, with no strong interactions between the liquid and the dissolved gas. Henry's law equation is very similar to Raoult's law. In the Raoult's law, you have recognized that the vapor phase composition is proportional to the liquid phase composition. Henry's law, the same. But the proportionality is a little bit different. Here total pressure the same as in the Raoult's law, but here is Henry's law constant. You could find the values from Appendix B5 of this textbook, or you could find some values in the internet or any database. Higher Henry's constant indicates lower solubility, because if you have higher values about the H, then you will have higher number of vapor phase concentration. It means we have lower solubility in liquid phase. It works well for nitrogen, CO2 dissolved in water. So nitrogen and CO2 is non-condensable gases and having no strong interaction with water. So the Henry's law could be applicable to these gases in water. Also, the solubility is very small. It does not work for ammonia SO2 in water, except at low concentration. So Henry's the law is limitedly applicable to the gases dissolved in a liquid. One more thing. You should know the difference of situation between Raoult's law and Henry's law. The left one is Raoult's law and right one is Henry's law. So here is the container for both cases, and in the Raoult's case we are thinking about the equilibrium, vapor-liquid equilibrium between vapor and liquid. If you have two components, you have two compositions in the liquid phase, also you have two compositions in vapor phase. However, for Henry's situations, gas is existing over the liquid and some portion of gas is dissolved in liquid. So here is the gas phase and here is the coexistent liquid and gas phase. So a little bit different. Okay, here is the simple illustration about Henry's law. A gas at 10 Celsius degree and 20 atm, total pressure, containing 98 mole percent nitrogen and 2 mole percent CO2 is in equilibrium with water. So let me try to the concentration or mole fraction in water of nitrogen and CO2 by using Henry's law. So YCO2 and YN2 was given to you like 0.02 for the CO2 and 98% for nitrogen. And if you know the value about the Henry's constant, then you could go to the composition of CO2 and N2 in liquid phase. I mean the amount of the gas dissolved in liquid or water in this case. So the Henry's constant of CO2 is 1040 atm and the Henry's constant of nitrogen is 66800 atm. and total pressure is 20 atm. So finally we could calculate the value about CO2 in liquid phase and nitrogen phase. As you know, a higher Henry's law constant indicates a lower solubility, so you could check it. Even if we have a lot of nitrogen in the vapor or gas phases, but the solubility of nitrogen is even smaller than the solubility of CO2 because nitrogen has very large value of Henry's constant. Also, for both cases, we have very small concentration of gases, CO2 or N2, in water. It means Henry's law could be applicable to this situation. So also remember that the mole fraction of He2O is close to 1.0 for both cases. Multi-component liquid phase equilibrium for extraction. Here we have three component systems. Organic solvent S, or water W, and the third component A. Case 1. Water and organic solvent S are completely immiscible in each other. And then in that case, the component A partitions were distributed between the two immiscible phases. Here is the schematic. The yellow is the organic solvent, phase 1, and the blue one is the water solvent, phase 2, and the component A is distributed between those two immiscible phases. You can find A in phase 2, and also you can find the same A in phase 1. We could define the distribution coefficient K sub D, distribution constant, is equal to the concentration of A in phase 2 per concentration A in phase 1. The distribution coefficient is the function of temperature and the identities of the third component A and the first solvent and the second solvent. So by using this kind of phenomena, you could extract the third component A from phase 1 to phase 2, or vice versa. Okay, still we are on the extraction about multi-component liquid phase equilibrium. Let me think about a more complicated situation. That is the case 2. Water and organic solvent are partially immiscible in each other. Here is an example. We have water as the first solvent, or phase 1, and the other thing is MIBK, the organic solvent, phase 2. And also here is the third component A. Mutual solubility increases in the presence of acetic acid. Acetic acid are soluble in both water and MIBK. Therefore, at low acetic acid content, we have two liquid phases. I mean, water is not miscible with MIBK at the low concentration of acetic acid. However, as the concentration of acetic acid increases, water becomes miscible with MIBK. So two liquid phases is going to the single liquid phase at higher acetic acid content. Here is the phase diagram about those three component mixture. X-axis is the weight percent MIBK, and y-axis is the weight percent acetic acid. The rest of weight percent is going to water. So, as I have said, at low concentration, at low concentration of acetic acid, water is immiscible with MIBK. So you have two liquid phases. However, at higher concentration of acetic acid, those two solvent molecules are miscible. So we are going to single liquid phase from two liquid phase. Between those two regions, we have a boundary. And this looks like dome, and the left heel of this dome is water-rich phase, and the right heel of this dome is MIBK-rich phase because we have higher concentration of MIBK. The intersection of the water-rich phase, sometimes called raffinate, and the MIBK-rich phase, sometimes called extract curves, is so-called plate point. I mean, the left side of plate point, on the borderline, we could find some water-rich phase or raffinate phase. Also, on the right side of plate point, you have MIBK-rich phase or extract phase. Let me go to the illustration about this phase diagram for further understanding. Let me try to read liquid-liquid phase diagram here. We have a mixture of 57 gram MIBK plus 10 gram acetic acid. I'd like to extract the acetic acid from MIBK, so I have introduced 33 gram water into the mixture. Then some portion of acetic acid is moving from the MIBK to water solvent. Then finally, the mixture of 57 weight% MIBK, 10 weight% acetic acid, 33 weight% water at 25 Celsius degree we have obtained. So where is it? 57 weight% MIBK around there, and 10% acetic acid. So we have the mixture at this point. This phase diagram is obtained at 25 Celsius degree. At different temperatures, we should redraw these liquid-liquid phase diagrams. Okay, so right now we have a point in the two phase regions. So this single dot or point would split into two ways. One is going to the raffinate phase curve, and the other thing is extract phase curve. And also, we in this case we should follow the tie line, not the horizontal line. We should follow the tie line. Okay. Then this point is going to the raffinate, and then finally you could find this one. And then let me read the weight% of MIBK. That is the 2.5% MIBK, and when we go to the y-axis, we could read 11.5 weight% acetic acid. So that is to say 86 weight% water we have for this raffinate. So we have specified the water dominant phase in terms of more the weight %. And then how about extract? let's go to the right side along the tie line, and then we could read the extract point for the mass weight percent for MIBK and acetic acid. This value is 86 weight percent MIBK, and let's go to the y-axis, then 9 weight percent acetic acid, plus we could calculate the last of them, which is 5 weight percent water. So here we recognize the values about the composition of extract phase or MIBK dominant phase. So it means some portion of acetic acid moves from this extract phase to raffinate phase. The value is 11.5 weight percent of acetic acid in water plus small amount of MIBK. So we could separate the acetic acid from MIBK. This is the method of separation, which is called extraction. Multi-component fluid-solid phase equilibrium, which is related to the separation method for adsorption. Here is the adsorbent, which is a kind of solid, very porous and high surface area material like activated carbon. And then let me put this adsorbent into water or some solvent containing some purity, some impurities. Then let me say that impurity or pollutant is called A. So the pollutant concentration is in liquid is XA. That is the liquid composition of A species. And this pollutant A is adsorbed onto the surface of adsorbent. I mean, the A moves from the liquid phase into the solid surface phase. Then let me say theta A is the surface composition of the pollutant A. Then there is an equilibrium between liquid composition and surface composition. By using this adsorption phenomena, we could remove some portion of A species in liquid by using some solid adsorbent. Here is two examples. The first one is phenol adsorption to carbon for water purification. Liquid mixture of phenol and water is in equilibrium with activated carbon. Then phenol adsorbs to the solid carbon surface. Phenol partitions or distributes between the liquid phase and the solid phase. The other thing is antibody adsorption to immunosolvent. In this case, this adsorbent is immunosolvent and antibody is adsorbed onto the surface of this immunosolvent. This is the isosum graph for describing adsorption. X-axis is the antibody in solution. I mean the concentration of antibody in solution, like XA. And y-axis is the amount of adsorbed antibody. So at the very first time, I means as the concentration of antibody in solution increases, the amount of antibody adsorbed onto the surface of immunosolvent would increase. However, at very high concentration in solution, the adsorbed amount of antibody is saturated. That is so-called the adsorption isosomes.